Okay, my name is Hanbek. I'm from Wisconsin-Madison. Honored to do a chair of this morning session. The first talk of this morning, very honored to have Professor Atsuo Kuniba from University of Tokyo. He's going to talk about boxable systems from integrable systems and probabilistic perspectives. Atsuo, please take on.
So thank you for the introduction, and I thank the organizers for generous invitation. I'm sorry for not being able to participate in person, but anyway, I'm happy to talk. So my talk consists of two parts, and part one is I deal with mainly type A case, which is known as the usual n-color box-ball system, and I would explain what the combinatorial Bethe ansatz is. And the second part is generalization from various perspectives. So this is probably what you are very familiar with. So this is an n-color box-ball system. And the N1 case is the very original Takahashi Satsuma automaton. And the N-ball case was also introduced by Takahashi-san in '93. So in my convention, which is slightly probably different from the original one, so the background is 0, and there are balls with color 1 and 2 and 3 for n equals 3 cases. And the time evolution split into 3 operations. The first, you move ball 3, and then 2 and 1. So each move I is pick the leftmost ball with color I and move it to the nearest light empty box, and do the same for the other color I balls. You can see that this, by the way, can you see my cursor here? Yeah, so you do like this, you do like this. So this is propagate stably. So namely, there is a soliton, corrective mode. It's a consecutive balls with increasing color to the right. And velocity is amplitude. So there are basically 2 ways to understand its integrability. The first one is probably argued a lot until in workshop. That's the ultradiscretization by classical discrete soliton equations. So I will mainly talk about the quantum integrability aspects, by which I mean that there is a Yang-Baxter structure behind it. So in that respect, it's a solvable lattice model at temperature 0. What does it mean? So the time evolution pattern, for example, is this, emerges from the configuration of a 2-dimensional lattice model in statistical mechanics like this, by forgetting the hidden variable on the horizontal edges. So here you only have the array of numbers, and these are on the vertical edges of this diagram, but we now have the extra degrees of freedom on the horizontal edge. So that's called carrier, which was a great invention by Takahashi-san and Matsudaira-san. So n-color box, well, you can immediately see that this is a configuration of the 2-dimensional vertex model. And original dynamics was described in terms of non-local operation, searching the nearest light empty box. But with this carrier variable, everything gets local because you can only describe the dynamics by the situation around the vertex. So it makes things totally local, which is very nice. So the n-color box ball system is a solvable vertex model associated with UQSL n plus 1 hat at q equals 0. So this configuration only survives in a certain good basis in this vertex model. And this configuration defines a low transfer matrix correspond to the time evolution of the box ball system. That's the story. So very quickly, I would like to summarize the situation. So we have a box ball system, which is a cellular automaton. So it comes, its evolution equations is obtained by the ultradiscretization of soliton equations. So in the broader sense, it's a non-linear waves, which is an integral system, classical integral system. On the other hand, we have the solvable vertex model having the Yang-Baxter structure, which I will call the quantum integral system. So it also arises as a Q0 limit of this system. So somehow this kind of inherits a nice features from the both sides. And actually the most notable such structure is the Bethe ansatz. So here you see that the most probably successful idea was inverse scattering method. And the universal way of solving the vertex model is known as a Bethe ansatz. And it was the insight by the Fadiev group in early 80s that this Bethe ansatz can be regarded as a quantization of the inverse scattering methods. So according to them, the Bethe ansatz, especially its algebraic version, is regarded as a quantum inverse scattering method. So somehow we should expect something like Bethe ansatz here. And what I'm going to explain is that actually there really is a very powerful approach here, which corresponds to the Q0 limit of the Bethe ansatz. So the main ingredient is the KKR bijection, which was invented in middle 80s. So I will explain, but basically it's a bijection one-to-one between two objects. One is linked configurations, another one is highest states. I will explain these things in a minute. So it asserts formal completeness of the string solution of the Bethe equations at the combinatorial level. So that was invented in 80s, so before the invention of the box-ball system. But it was discovered that this really has something to do with the box-ball system in 2003. So let me explain what's happening. So here is the simplest example of a spin 1/2 periodic Heisenberg chain with length L side. Now, if, for example, you consider the 6-side chain in 3 downspin sector, the Bethe equation is like this. So this preserves the total upspins and downspins. So you can concentrate, for example, the 3 downspin sector. And then you should solve this simultaneous algebraic equation, which is known as the Bethe equation. So the basic problem is how many solutions should we have? And there should be 5 solutions for the completeness. So this 5 is a Kostoko number, and which is a multiplicity of irreducible representations in the tensor product. So it is known that Bethe vector associated with this Bethe roots is highest with respect to the global SL2. And this Hamiltonian commutes with the global SL2. So once you capture all the highest weight states, then the other vectors can be generated by applying the global lowering operator of SL2. So for completeness, you should have 5 solutions to these Bethe equations. So the 5 is number of the highest states. And what is the status? So actually, there are 5 solutions, which is displayed like this. So these dots are U1, U2, and U3 on the complex U plane, which is rotated 90 degrees. So actually, this vertical axis is the real axis. So do you observe something? So somehow these Bethe roots, 5 solutions, are described, at least approximately, as the collection of strings. What is strings? It's a 2I equidistant configuration, symmetric with respect to this vertical axis. So this is strings of length 3, and these are the strings of length 1, but there are 3 of them, and this solution contains strings length 2 and strings length 1. So I said that the KKR bijection is the bijection between 2 objects. Now I can show you the example of the simplest example of the linked configuration. They are like this. So you see that this is obviously the combinatorial analog of the Bethe roots. So this diagram represents, this Young diagram represents that there are three strings, length 3 strings here at position 0. And there are 1 strings, and there are 3 of them, and all at position 0. In these 3 examples, so there are 1, 2 string and 1 string, but their relative positions can vary. So those are distinguished by these numbers, which are called leading. So these are the one side of the KKR bijection, linked configuration. And what about the other side? So Bethe ansatz is a procedure to construct the Bethe vector, eigenvector of the Hamiltonian, given the solution of the Bethe equation, namely the Bethe roots. So these things should be a combinatorial analog of the Bethe vector. So Bethe vectors in general should be the very complicated complex coefficient superposition of the spin up-down states. But because we are in a combinatorial setting, so those vectors should be replaced by the word of 0 or 1, spin up or down. And here is the image by the KKR bijection. Those green words of 0 and 1 as a combinatorial analog of the highest weight vector, which I call highest states. So this is the simplest example of the KKR bijection, which is not true. Now, let me jump to the SLN+1 situation. So the streets are basically parallel. So we should have the bijection between highest states and leaked configurations. For n equals 3, the correspondence, one example of the correspondence like this. So now we have got the color. So not only the one Young diagram, but we have 3 Young diagrams corresponding to n. And each Young law has got the numbers called leaking, which specify the relative position of the string of individual colors. So these are the list of the lengths of the strings of color 1 and color 2 and color 3, so on. And these green numbers specify its kind of position. And the image is like this. So this is a combinatorial analog of Bethe roots in SL4 spin chain, Sutherland Women's chain or something like that. So these combinatorial objects accommodate the solitons in BBS. And these strings are these objects, linked configurations, is a combinatorial analog of the Bethe roots. So physically, these strings are the bound state of magnons. So I said highest states. This is slightly a technical condition, so you don't have to care much about it. So this is the highest condition is expressed by this, but you don't have to care much about it, actually. And what is the general linked configuration? It consists of 2 parts. The red part is a collection of n tuple of Young diagrams. That part is called configuration. And each row should have its leaking integers. This part of data is called leaking. So in total, it's called linked configurations, which I do not like this. So this mu I is a Young diagram, and row Ry is the set of integer arrays indicating the numbers assigned to each row of mu I and so on. And they should satisfy certain selection rule, which I present in the next page. So this is a bit complicated, and actually precise detail doesn't matter, but I will probably use this notation also tomorrow. So let me just introduce it. So let's look at the S Young diagram, S part of the linked configuration. So first of all, there should be Young diagram, which I denoted by mu A. And let MAI be the number of the length I rows. So MAI is the length I rows in mu A. So by the definition, this summation equals to the total number of boxes in this Young diagram. And the selection rule is like this. So this leaking should be ordered in this manner. Well, it doesn't matter, but anyway, it should obey this inequality with certain upper bound, which is also important. This upper bound is given by this formula, where L is the length of the chain, and C is the Cartan matrix of SLN+1, and with this linear form. So a good thing about this combinatorial object is counting formula is immediate. So because this condition is seemingly independent for each choice of A and I, and because of this inequality, you can immediately write down the counting formula with a number of the linked configurations with prescribed kind of mu A's configurations like this, because of this identity, this binomial quotient. So for historical reason, this kind of counting or formula is called the fermionic formula, and this is fermionic selection rule. Well, maybe I should say a few more words. So Bethe roots should not collide. So then it will lead to the zero Bethe vectors and that sort of things. So there should be some kind of fermionic repulsion among Bethe roots. That's reminiscent of this condition. So because of that, where people like Kirillov called fermionic and so on. So we are succeeding his terminology. So this is a SLN plus generalization of Bethe's very original formula for the number of string solutions in his very original paper. Let me show you the relevant part of the Bethe paper. So this is our P, and N is L in our notation, and this Q is M. And you see that in coefficient of this Q is the minimum of N and P because of this inequality. The minimum of N and P, what is P? P is the summation index, and N is outer index. And if you look at this formula, So this coefficient is I is outer index and J is summation index. So exactly that matches. And also he has coefficient 2. And if you look at this, and we specialize to the SL2 case, this 2 is a very well-known matrix, 1x1 matrix of SL2. So exactly this reduced to the Bethe's formula. And this is very natural thing, SLN generalization. So he wrote down this formula. So that's the original Bethe's formula. It's a natural generalization by SLN as well. But so far, I haven't said a word how to obtain this map, how to find the image from in these directions. So that's actually the content of the KKR bijection, and which is very messy. So I'm not going to explain every detail, but try to convey the flavor of it. So given linked configuration like this, so the algorithm tells you that there are certain boxes that should be removed. So those boxes are indicated by blue boxes. So the algorithm is designed so that after removal, the remaining object again becomes a linked configuration. Namely, it also satisfies the selection. So you can repeat this removal procedure until you end up with trivial linked configuration. Every time you remove those boxes, you record the numbers, which is the number of boxes that was removed minus 1 in this convention. So I removed 2 boxes, then I record 1. And I removed 3 boxes, so I recorded 2, and so on. In this recording number, red recording number backwards, you obtain the image. It's pretty messy, complicated, and very easy to make mistake. It's sequential, kind of. But it's mathematically perfectly well-defined algorithm, and you can program it on computer, and the computer gives you back the answer almost instantly, even for the highest states of length, say 100, so on. Anyway, that was the KKR's invention. Let's turn back to the BBS. So now we have the bijection between highest states and linked configurations. And if you have many zeros and certain arrangement of the solitons, then those are the highest states. Actually, this highest condition doesn't matter essentially, but anyway, then we can observe the dynamics of BBS through the lens of KKR bijection. So we can translate the dynamics into the dynamics of the linked configurations. Now here is the answer for this example. So here you see you observe some remarkable feature. So these configurations, Young dynamics is conserved. It doesn't change at all for all these time intervals. And moreover, this leading flows linear. That is, the KKR bijection linearizes the dynamics. In short, linked configuration is nothing but the action angle variable box-ball system. So the KKR map gives a direct and inverse scattering map, and linked configuration may be regarded as the scattering data, which separates the BBS states into the amplitude and phase of solitons and so on. Especially in this example, you have solitons of amplitude 4, 3, and 2, and that can be observed in this Young diagram. So mu1, the first color part of the linked configuration, gives a list of the amplitude of soliton. Well, at this point, when we discovered this fact, it was very kind of astonishing and we were very happy. But now, in retrospect, something not so satisfactory because we don't have time evolution in this rigging, and also the meaning of these Young diagrams is rather implicit. So it can be only known after doing the KKR bijection and so on. So somehow there is no democracy among these parts of the linked configuration. I mentioned this because I will come back to this point later in part 2. So please remember this non-democratic feature. this part is especially treated as a simple kind of, especially exceptional things. Anyway, so now we know that linked configuration is action variable BBS. That's the main conclusion of the KKR theory in the context of BBS. So now let's turn to the tau function. So I said that highest states. So that's a labeling, combinatorial label of the highest weight vector or highest weight or or module appearing in the tensor product of spin chain states. So that's a very kind of well-studied object in algebraic combinatorics and combinatorial representation theory. So there is various combinatorial labels, equivalent labels. And one of them is semi-standard Young tableau. And actually, there is a semi-standard Young tableau. You can attach the integer, non-negative integer, known as Lask-Schutzenberger charge. And there is a KKR theory interpretation of it, which is given by this formula. So if you interpret this LS charge in KKR theory, it is expressed by this formula. This is also the result of KKR. So the notation is like this. So as I explained, these are the Young diagrams, and these are the riggings, and notations like this. So it's a kind of quadratic in the sense of ultra-discrete. Anyway, so this is Lask-Schutzenberger charge. Now, using this function, which is I regard as a function of data mu and r, I introduce the ultra-discrete tau function by this. So it's a minimum of this function plus some additional term, simple term, over the power set of the Richt configuration. So here I regard that the Richt configuration as a collection of the strings of various colors and lengths, which has got its own rigging. So for example, the one choice of it is to choose these three blue strings and so on. So here we have 1, 2, 3, 4, 5, 6 strings of color 1, 2, or 3, and the length 1, 2, or 3. So there are 6 strings in total. So this minimum extends over 2 to the 6 possibilities. So it's a perfectly well-defined kind of piecewise linear function. And obvious choice is empty choice. You don't choose anything. So then that choice gives you 0. So this is minimum of 0 and something else. So this minimum should be non-positive. So if with this minus sign, this tau becomes non-negative integer, right? And the scale dependence is enters through this choice, mu0. So mu0, I haven't explained I haven't explained kind of in detail, but this part corresponds to this part. Anyway, so this is a double index kind of UD analog of tau function. That's only the definition using this LS charge formula for in KKR theory. And now comes the theorem. So this tau ki admits the following characterization. First, it is the ultra-discretization of tau functions for KP hierarchy. Second, it's a corner transfer matrix of the box-ball system. So let me explain these things. The first, so the tau ki can be obtained as the ultra-discretization epsilon logarithm with something which is very finely chosen depending on epsilon. So KP tau function, probably many of you are familiar with, but it's a expectation value of the exponentiated quadratic form of the free fermions, which has got amplitude C and momenta P and Q. So there is a very fine tuning of this amplitude momenta of the free fermions so that this UD limit exactly gives this formula. So this expression is not totally positive, but it's fine-tuning. There is fine-tuning to achieve this. I remember that there's some comment in Tsujimoto-san's talk, even the sum expression is not totally positive. There is a certain case you can extract certain non-trivial kind of ultra-discrete limits. And this is possibly in this example. By the way, this I is a certain vacuum in fermion Fock space indexed by I. So this is the first. So the corollary of this first thing is you can corollary first thing, one is ultra-discrete Hirota bilinear equations. So as you know that this tau, original tau function satisfies the Hirota bilinear in the usual sense. But because of this origin, so this UD tau function satisfies the Hirota bilinear in the sense of UD. So the multiplication is replaced by plus, and plus is replaced by max and so on. So with some constant here. And here tau bar is tau ki associated with Richt configuration with one-time evolution. This one-time evolution is defined by the commutativity with respect to the BBS time evolutions. So this is the content of the first assertion. And let me explain the second assertion, corner transfer matrix. So suppose you are given the Richter configuration and apply the KKR bijection, obtain the BBS states or highest states, B1 to BL. On the other hand, as I explained, we can construct a UD tau function like this, Ki. Then this Ki, as I said, non-negative integer, has a very concrete meaning like this. So this K, I take the first K portion of this local state and let it evolve by the time evolution T infinity of the BBS. Then there should be a bunch of balls, various colors in this quadrant. And I count the number of balls in this quadrant, where especially the first row, the expression, I only count the number of balls satisfying this color condition. So it depends on the quantity, depending on K and I. So K is a kind of space index, I is color, kind of color index. So because this is associated with the quadrant of the 2D lattice, it's an analog of the Baxter Corners transform matrix. So, well, there are more reasons, but let me omit it. But anyway, so from my personal point of view, so among many great inventions of Rodney Baxter, I think that this corner transform matrix among the top 3 in my personal viewpoint. Anyway, so now we have the very concrete interpretation of this UD tau function in terms of the number of balls in BBS. So then with respect to such knowledge, if you look at this again, then you immediately notice that this is nothing but the evolution equation of the BBS. So certainly this counting satisfies the certain piecewise linear bilinear equation, and which is nothing but the BBS. So now let's come to the corollary of 1 and 2. So we have a piecewise linear formula for KKR map. So given Richter configurations, we should obtain the array of BBS states where each BI is the one row semi-standard Young tableau. And this number of entries of this form where this KXKI is explicitly given by the UD tau function by this formula. So as I explained, this KKR map is very messy and easy to make mistake and sequential. So it's very hard things to know, but there is a single line expression for this. That's kind of remarkable. And that's a manifestation of the integral. And as a corollary, so as I said, mu R, Richter configuration is an action angle value of the box ball system. So that means this provides you gives you the explicit general n soliton solution of the n color BBS with arbitrary inhomogeneous box capacities. So this box capacity I haven't explained so much, but this appears here. So in probably Tsujimoto-san's talk or someone else's talk, there is 1 minus or minus 1, something like that in such a sort of equation. That has been replaced by this integer data. So that corresponds to the capacity of the case box in the BBS. So that can be arbitrary. So that's a general solution. So as a schematic summary, we can say like this table. So in combinatorial version of a Bethe ansatz, so the main object is a Richter configuration, and it plays a role of action angle variable.
日本はカーボンプライシングと投資支援の組み合わせにより、まず国内において、今後10年間で150兆円の GX 投資の実現を目指していく。そしてこれをアジアに拡大をしていく。そしてアジアのこの膨大な GX 投資の
Is it now okay? Is it okay? And can you see this? Hello, can I continue?
Yeah, sure, yeah.
Yes, please.
Please.
Yes, please.
So can you unmute yourself?
Kuniba sensei. Okay, that's fine.
Okay.
Right, great.
Sorry. So I'm not sure what's happened. Anyway, so could you hear until I say about this? Maybe I can continue from this table. So in Bethe ansatz or combinatorial version of it, the main combinatorial object is Richter configuration, which plays a role of action angle variable in box ball system whose dynamics is linear. On the other hand, another essential tool from the solver lattice model theory, that's the corner transfer matrix. And the main object is the charge. and it plays a role of a tau function, and the dynamics is bilinear. So I think this is the end of the part one, and maybe it's I may be able to take or better to take some question if you have any at this stage.
So it's Vincent. Just a question about. I mean, I did not understand when you put time on the ridging. It's only the first Young diagram which is affected, not the others, or this is general. I did not understand why.
Yeah, hello, Vincent. Yeah, thank you for the question. Yeah, you're asking about this. You're right. So this is just to, I increment this rigging by this rule. So the coefficient of t is just the length of the row. So
just you said there were, I mean, there are some equation, for example, you can make product of Baxter matrices or something like that. Is it the same with the tau function? You can make somehow this product of 4, say.
Yes. You mean corner transform matrix A, B,
yes.
C, D trace or
yes.
something like that. Actually, this is the UD analog of that. You see for CTM. And A, B, C, D, among the 4 of them, 2 are kind of inverse. So this is really the UD analog of the Baxter's formula. So as I said, this tau counts the number in these quadrants. So if you take the second difference, you can obtain this local state at the corner. That's this formula is doing. And that's correspond to the UD kind of analog of the Baxter's formula of the local states. It's a trace sigma 1 ABCD divided by trace ABCD.
Hello, it's Robert Weston. So the corner transfer matrix is, clearly a very important object in solvable lattice models.
Yeah.
But nothing like the bilinear relation seems to appear in solvable lattice models. Can you understand that in that language?
Oh, that's a good question. I haven't thought about that. Well, yeah, very good question. Let me think. So yeah, immediately I cannot answer. Yeah, but that's a good point. Actually, I remembered my paper here. So there is some, well, if I replace the corner transfer matrix by the kind of corner transfer matrix energy, then we can certainly prove this identity. Kind of. So because this tau is essentially the charge or crystal energy. So this can be proved. And actually this proof of this theorem uses such fact. That's all I can say. So now let's go to the part 2, the generalization from various perspectives. So this is an usual, natural kind of routine things that what happens for the other affine real algebras. So what we did is to play the same game for the KR crystals of this non-exceptional affine real algebras. So this KR is killer of Reshetigin, but actually these crystals are constructed by people like Kang, Kashiwara, Misra, Miwa, Nakashima, Nakayashiki in early 90s. So there are time evolutions, family of time evolutions. Among them, T infinity is especially simple, which I denote by just T and associated energies. And that's a particular particle system with pair creation and annihilation via bound state. And solitons exhibit the factorized scattering with S matrix. And this S matrix can be proved to be identical with the combinatorial R of the affine real algebra with 1 rank smaller. Because 1 letter is preserved for the vacuum. So the soliton degrees of freedom, you lose 1 letter, which is reserved for the vacuum notation. So the other letters can still behave and as a soliton. So it can be S matrix is the combinatorial R with 1 rank lower. Well, this proof of this is still non-trivial, but anyway, so this is an example from the SO10 hat, which is D15 in this notation. So you see that the collision of 2 solitons of amplitude 5 and 3 comes back certainly the amplitude 3 and 5, but you see that 3 bar pair here has been replaced by 4 and 4 bar pair here. So what's the origin of such kind of pair creation and annihilation? Well, actually the key is the following theorem. So T that's a T infinity, is a translation in extended affine group. And that's as on general grounds expressed as a product of simple reflection and some Dynkin diagram automorphism. So because this part, its theorem is slightly technical, but it has something to do with a Pitman's transformation. So let me try to explain a bit more in detail. So in order to compute the action of simple reflection in crystal setting, so I need to introduce the signature law for the simple reflection SI. So for SL3 example, SL3 hat example, here is a crystal graph, it's a color-oriented graph. And this 1, 2, and 3, those are the local states in the box-plot system. Sorry, I changed the notation. It's not 0, 1, 2, but 1, 2, 3 in this page. And it's a color-oriented because these arrows are colored by 0, 1, 2. And I assign the signature, 1 signature, 2 signature, and 0 signature in this manner. So basically, in this simple example, just the source of the color 2 is plus in 2 signature, and the target is minus in this signature, and so on. So our task is to compute the action of S2, second simple reflection to this BBS states or kind of tensor product of these B1 crystals. So what you do first is assign I signature. So in this case, I assign 2 signature. So 2 signature is plus for 2 and minus for 3. So minus, minus 2, plus, plus, minus, 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 plus. And then what you do is eliminate plus, minus recursively. I would call this singlet pair. That's SL2 singlet in a crystal setting. So, but this elimination should be done recursively. So first I remove this adjacent singlet pair, and then this plus and minus becomes adjacent. So I remove this. And then I end up with minus and then plus. So one should always end up with this pattern with alpha and beta, which can be 0 in some cases. So in this case, alpha is 3 and beta is 1. And now the image is determined by exchanging the number of minus and plus signatures. So because these signatures in the parentheses already eliminates, I don't touch them. So what I do is to replace this minus, 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 plus by minus, plus, plus, plus. So that means I keep this 2 at the end and this 3 at the end, but this 3 must become 2 because plus signature, plus 2 signature means this state 2, and here so on. So this is a way to determine the simple reflection. So you see that this successive elimination plus minus structure is essentially Pitman transformation. If you attach upward step to downward step to minus and upward step to plus, then you have, well, certain paths. And in Pitman's transformation, you have certain portion, a segment of the path which should be reversed vertically. And this reversed part is essentially correspond to this non-touched part. So if we change the interchange the eliminated part and the non-eliminated part, it actually becomes Pitman's transformation. So that's represented by up to gauge. So let's do this exercise for SL3 hat case. So in this case, the theorem has this form for the BBS. So I first apply S0 by the signature rule using the 0 signature, and then using 2 signature, I apply S2. And this sigma, this is the Dynkin diagram automorphism part, the cyclic Dynkin diagram automorphism. You replace everything by A minus 1, so like this. So you see that this image of this BBS states with 1 is regarded as a background is exactly like this. So you reproduce the T infinity dynamics in this manner. If we insert the trivial 1 here, because S0 square is 1, where little s is a simple reflection within each component. So then you remove, then you notice that this factor is the move ball 3 part of the algorithm, which I showed in the very beginning of the talk. And this is move 2 part of the algorithm. So in this manner, this T infinity dynamics consists of the ball split into the ball moving algorithm for various kind of balls. That's really originates in this fact. Translation in extended affine group factorizes in this manner. So this is a kind of interpretation of the Pitman's transformation. But so for simplest BBS in Takahashi-Satsuma automaton, you just repeat the Pitman transformation again and again. But for higher rank case, for example, in this case, so first I apply S0. That means I do the Pitman transformation between 1 and 3. And after that, I apply this. That means I apply Pitman transformation between 2 and 3. So this combination effect can result in something different and non-trivial and interesting. That's a higher rank effect of the Pitman transformation. And it's not just interpretation of Pitman's interpretation, but it's kind of generalization. For example, if we consider the SO8 hat, T14, then the crystal graph takes this form. So this is SO8, 8-state PBS. So 1, 2, 3, 4, and bar of them. And interpretations, one is empty box, and one bar is bound state, and the others are particles or antiparticles. And this is the general form of the factorization of the translation in extended affine Weyl group. And it can be gauge equivalent. It is gauge equivalent to this operation with K's as a ball moving algorithm. So what is the algorithm? So first we replace this one bar. So do a kind of bar of the empty background by a pair J and J bar, where J is the specified particle or antiparticle within the box. And these 2 and 3 are the same with the usual BBS algorithm, except that target box of the move is not only the empty box, but can contain the antiparticle. That's the difference. Anyway, if you finish this procedure, then replace a pair J and J bar by one bar within a box. Here is an example. So given this state, I replace one bar by two and 2 bar pair, particle antiparticle pair, because this index is 2. And now I start doing the BBS moving algorithm. And so I pick 2 because this index 2 and try to find the target destination, and not empty box, but this 2 bar can welcome this 2 because this 2 and 2 bar is opposite. So it can sit here. And then I pick this particle, but now these pairs are kind of self-satisfied. So I overtake them, I have to overtake them, and it has overtake them, and it goes here. And that's the end of the procedure 2 and 3. And after these are the pairing, then I close it as a 1 bar minus. This is the end of the K2, but now it's followed by, oh, sorry. Well, let's imagine that it was K3. Then next I have to replace this by 3 and 3 bar. So this combination effect is really non-trivial, and it results in a very interesting dynamics, which is factorized. So as you see that the usual BBS corresponds to the special sector of such BBS free from antiparticles. So somehow BBS is contained, it's more general particle antiparticle system. So that's one kind of generalization and relation to the Pitman's transformation or generalization of it. So another generalization, that's a quantized BBS. So this is a usual diagram for the transfer matrix of time evolution of the box ball system, T infinity. And so it's, of course, described as a carrier. So this M is the load of the carrier. So let's write down the amplitude using the Kronecker delta. So if M equals 0, so the load of the carrier is 0, then it just passes through. Well, by the way, this 1 is empty box and 2 is a box containing 4. So everything is empty, then it's allowed. So amplitude 1. So when M is 0, this is 1. But if M is greater than 1, then you must drop one of the box and it must become this form. So this must vanish, but instead this happens. So this is a Kronecker delta, amplitude expressed by Kronecker delta. And now the quantization in this sense is given by this. So when Q equals 0, it goes back to this formula. So well, there are infinitely many ways to invent such formulas, but this formula, red formula, is not written capriciously. So it's have some decent origin. So let me explain. So the transfer matrix, well, as I said, the time evolution of transfer matrix of a BBS should come from the transfer matrix of such spin chain setting, where the quantum space is spin 1/2 and auxiliary space is spin L/2. So if you just say that this is a quantization, that's boring. You just go back to the original vertex model, which is boring or well known. So what we did is to compute the special limit of L goes to infinity, because I'm interested to the T infinity, staying within certain asymptotic domain. What sort of asymptotic domain? So it must be compatible with the one background. So this carrier becomes infinitely large, but I keep the finitely many load in it. So the empty space becomes large, infinitely large, but I retain the finitely many load of the box. In such asymptotic domain, the limit can be computed by using the fusion and so on, and the result is this. So this is some another remark, but I wouldn't tell much about it. So this is a first of the theorem. The second theorem, this dynamics has some curiosity. So let's write down the action of this quantized BBS dynamics like this, where ABC is the amplitude, where B is the initial state, monomial state, and C is the output states like this. So then the second claim of the theorem is amplitude satisfies orthogonality and linear norm is preserved. That's strange and curious. So here is an example of this identity where B and C is equal. So you should have this equality. So I apply this dynamics for the two soliton states. So length two solitons. So there are various possibilities that you have in the downstairs, because this dynamics doesn't vanish like this, but has an infinite tail. So this is an infinite sum, but somehow it becomes polynomial after taking the geometric series. And non-trivially, the summation of these quantities becomes 1. So somehow by choosing these pieces arbitrarily, you have infinitely many, generator of infinitely many series and identities. That's curious. But I have to confess that I haven't found good, interesting, or fruitful application so far. So actually, this result is quite old, but this is my first opportunity to talk about it in public. Anyway, so it's just curious. That's another generalization, and BBS with reflecting end. So this was already mentioned by Okado-san. So I will be just brief. So, oh, it's time. So, well, it's really time. I'm sorry. So let me just skip it, then show it. So this is a complete BBS. But I'm afraid I don't have time. Maybe how many minutes do I have? 5 minutes, okay?
Yeah, 2 or 3 minutes, please.
2 or 3 minutes, okay. Yeah, so so this is original BBS. But if we try to apply this kind of time evolution with k greater than 1, this carrier brings the sum balls take away to the infinity, which is unsatisfactory. But if we design the local states in this manner, namely complete set of fundamental representation built in, then you can apply any time evolution, and solitons become labeled much simpler labels, and the scattering becomes completely diagonal. But so we can apply the GHD machinery and so on. And every part of the Licht configuration has a direct interpretation. So the complete democracy of the Licht configuration is achieved. This is, the Gregoire and Bansan is in the audience, I think. Yeah. So this is the example. So the solitons just labeled by 2 index, color and length indices, and this phase shift. And this is completely kind of diagonal scattering. And this is the final example. So this is a duality with combinatorial system. So if you take this crystal, we are fixed L1 and LL, then you can apply the SL, this is SLN hat crystal. Of course, you can apply the while group of SLN hat. But also you can apply the SL hat, where L is the system size, by changing the K and K part by the combinatorial R. And it turns out that these two affine Wald group is commutative. So within each extended affine group, you can construct a translation like this. Especially this YK, the construction becomes this diagram. And this diagram was appeared first probably in Yan's paper in 1969, and he immediately pointed out this commutativity. Anyway, in this picture, because they are commuting, so they are their picture. So if you regard TA as the dynamics, then the commuting another Wald group as a symmetry or background transformation somehow. So somehow the pictures are interchanged. So this is an example of the combinatorial Yan's system where the time evolution like this is achieved like this. So playing in the Yan system, you don't bring the extra carriers, but at certain time, one of the box ball system decides that I'm going to be the carrier for everybody else. And then he starts to steer the others as pretending that he's carrier and comes back to the original position. Then that provides another time evolution. See, that's the Yan system. So I didn't have time to talk about the periodic system, but it can be, you can find many interesting results in these references. So this is the end. Thank you for your attention.
Okay, is there any question from the audiences?
Thank you. So your quantization procedure involved this limit in this asymptotic domain. So that starts to look like a lot like Baxter's Q operator. Is that a useful observation? Or?
Yeah, I understand the comment, but I haven't found a kind of application to such connection. So maybe that's the future theme, I think. Yeah, thank you for the comment.
Maybe it's more a comment than a question, but the first Jung tableau, you have nice interpretation as with solitons. But for the others, it's a bit mysterious what they mean.
So in this non-complete BBS, it's mysterious or, well, it's meaning indirect. Somehow, so it's an arrangement of these colors, represents the arrangement of these colors. So the solitons in a higher color sense. So I can only say such a vague description. But in this complete BBS, which Vance and you and I and Gregoire did, so it has a direct interpretation. So this color A part is a number of the list of the number of the solitons of this. So it's very direct. In that sense, there is no kind of special color which is evident. So in that sense, democratic.
Is there any question for the online audiences? Can I ask a quick question? So thanks a lot for the great talk. I have some question about the quantized system as well.
Yeah.
So can you go back to the vertex model? Here. So it seems like I'm thinking to interpret this Q to the M as a probability content. So it looks like
I have a minus sign here.
Oh, okay.
Yeah, I cannot remove this minus. Yeah, that's I had some similar question when I talked about this.
Okay, so we'll think about it more.
Yeah, unfortunately, this minus cannot be removed.
So I've been thinking about erratic carriers where there's an epsilon probability that
Sorry, I couldn't catch you.
So I thought, I'm studying a version of the usual BBS where there's an epsilon probability that the carrier can miss picking up a ball or miss dropping of a ball. So in that case, there's a fixed probability of doing something abnormal. But it seems like in this case that abnormal probability is also depending on how much load you have. Like a M is your current carrier load. So this stochasticity of the carrier seems like it's depending on like how much it has currently. So it's interesting to see that.
I see. Yeah, good to know.
Yeah, okay. So thank you. Let's thank the speaker again.
Thank you.